We are now with our final presentation, which will be given by Bryan Palmintier, who is the group manager for the Grid Connected Energy Systems Modeling Group and the principal engineer at NRO. His research focuses on effective integration of distributed energy resources into both the distribution and transmission grids through advanced integration tools, simulation, and analysis. Earlier, he worked at RMI, consulted in energy efficiency, built satellites and rockets, taught mountaineering, and got a few too many degrees from Georgia Tech, Stanford, and MIT. He will present experience developing large-scale synthetic US-style distribution test systems. Bryan, you have the floor. I would like to make it, up to now, we have been perfectly on time, so let's keep that track record.
Excellent. I'll do my best to keep us still on track. I'm guessing everybody can see the screen. We're going to go ahead and, as mentioned, talk about some experience we've had developing some large-scale synthetic distribution test systems with US style. I wanted to first acknowledge that this has been a very large joint effort, both with colleagues at INRAL as well as with partners at University of Comillas in Madrid, Spain, and MIT, and you'll hear a couple other folks along the way. Before we get too far into this, though, I wanted to just highlight that this talk's a little bit different than what we've heard throughout the rest of the session. Part of the reason for that is that we'll have equations and formulas and talking about how to develop the next new algorithms. Rather, we're trying to provide a large-scale realistic framework to try to answer some of the questions that people alluded to in terms of, hey, it'd be great if we could have some base systems to actively work on that have the right scale and more diverse and all those kind of pieces. The other sort of highlight here is that I'm going to talk about sort of our experiences. So we'll go through and I'll tell you what we've been doing, but along the way, we're going to take a break and talk about some of the lessons learned and other approaches in case you might want to do something like this yourself, or just to kind of understand a little bit more about what's going under the hood with these types of approaches. So first off, motivation for this is, I imagine if you were trying to build a new, direction algorithm like Google Maps or something along those lines, having a little bit of we're not wanting to advance mode. There we go. But all you have is the sort of cartoon maps that you might get from a hotel or a tourist agency. And as many folks are aware, in some ways, that's kind of where we are with publicly available power grid data, particularly at the distribution system level today. There's certainly some exceptions, as we've heard for some examples, but for the most part, today's test systems are really just a single feeder. Some of them are small, and most of them are not fully complete in terms of having all the data you might need for some of these algorithms, as well as to look at sort of realistic cases around loads or secondaries or other aspects there.
Bryan, did we intentionally lose our slides?
Uh-oh. Nope.
Okay.
Shoot.
Just checking.
I will reshare. Resharing. Something strange happened. Not sure what happened. Did you have you seen any of them?
we saw the first slide.
Are you able to see them now?
Yes.
You're still on the first slide. You saw the first slide?
Yes,
right,
we did.
Here's a pretty animation versions of these things. You're trying to build something like this. All you got is these kind of toy maps. And the challenge is that's kind of where we are today with distribution test system data. And that's quite different than what you would see with real distribution systems, where the feeders are interconnected. The interactions from one through a substation, shared transformer to the other can be quite important. Reconfigurations we've talked about before, a much larger scale than we find in the test systems. That's not to knock the test systems. They served a great purpose. They helped us test out, make sure that power flow solvers worked right and things like that. They did what they were designed for, but we kind of need something new. And in particular, a couple of problems that come up. I mentioned this idea of small scale and limited. Like if you show your algorithm works on the 123 bus system, and most real distribution systems are an order of magnitude or two larger, it's still a big gap before you can get so much credibility beyond the academic community. But the other thing that's a really big challenge, which I think was started to see a little bit of even within the presentations here and elsewhere in PSCC, is that most people end up, because these things don't have enough definition of the aspects like distributed resources or yet load details that you might want to look at, everybody starts with a test system and kind of makes some modifications for their use cases, but that means you're never really able to compare apples to apples. And then the other approach, of course, to get this real scale data is to have some sort of legal non-disclosure agreement with a utility data partner, spend what could be, in some cases, lots of money to work with those pieces to get them to be in a clean, usable form, and then be unable to really share that more broadly with the research community. So ARP-E recognized this as a challenge and funded a whole bunch of different projects in this general area, most of which were on the transmission space. But we focused on a project called the SmartDS system on doing so for distribution systems. And in particular, making large scale, so we're talking, like an entire metropolitan area with hundreds or thousands of feeders all interconnected with each other, and including all the details from, in our case, high voltage down to low voltage systems, and making those realistic but not real, kind of as if another utility had come in and built a system there, but it still acts in the same way that a system would really work, to be able to do some of these test cases. And so, that's what we did. I'm going to talk through a little bit about what we've been doing there, and at the end, we'll talk about some of the use cases we've built so far and some things that are going on. So here's some steps of how we do this. So the first step is to build up the loads, and then you build up the electric models and kind of refine those a bit, double check things are okay, and then add some scenarios. So kind of talk through how this looks. There's you'll see a few references that pop up for more detail on some of the aspects here on the side. So in this particular case, we wanted to make sure that we have geo-referenced information, which is very helpful for things like doing integrated grid and transportation studies and looking at solar radiance or other kind of aspects that matter where the location is. So we purchased some parcel data, which tells you about the land usage and the buildings in each particular area, and use those to get an estimate of a planning load, along with street maps, in this case, OpenStreetMaps. That allows us through a tool that was adapted from European use, but is now being used here in the US to build up distribution transformers, locating those, and then building out low voltage network. So just a quick note, these are US style systems. So our low voltage networks tend to be quite small, serving sort of 1 to maybe, in some cases, a couple dozen, but typically no more than that customers. These are really just small little cans out on a pole or boxes in people's backyards that serve a couple of houses. So quite different than you might find in Europe. And then from there, we can build up distribution substations to build out the medium voltage topology. And wait, I was supposed to tell you how this stuff works. So let's go back and talk about that a little bit more. So here we go, customer data. What did we learn about that sort of piece? If you've ever had a chance to work with parcel data, nothing's quite that standard. And so a couple of quick things to pass on. One was, it was important to be able to map the codes used in the parcel data to the codes used in buildings and other formats. And we had to develop sort of a standard mapping framework for that. Also, parcel data sometimes outlines the lots, kind of the land owned by a building or its neighbors, versus just having a center point. And kind of working back and forth between those was something that required some care, particularly matching buildings to centroids when they weren't within an outline because the outline wasn't available. And then finally, we used a wide variety of data sources for existing load levels for both residential and commercial buildings that had a certain scale, but in the real world, there's some things that are outside that scale. So it was important to be able to basically extrapolate linearly behind by entering a zero. We used sort of volume of the area. So putting in a zero volume building as well as a very, very large style building. So we could always make sure we had an energy metric within that space. Distribution transformers were reasonably straightforward, but there was a good bit of work that was required to understand the secondary styles. This is the low voltage network. Or low voltage system. In case you're wondering, these are not mesh network secondaries, as sometimes happens. These are just low voltage systems. And initially, the approach was a simplified one that's often used in these when the data is not available, because most distribution utilities, at least in the US, don't even capture any representation of the low voltage net system at all. And that's sort of just taking a star arrangement, going from the locations to the distribution transformer. We also experimented with a tree arrangement, and through a combination working with experts, as well as like literally walking around in different systems here in the US in different parts, we ended up settling on a hybrid approach where some things are connected in a star way, but others are connected in a tree way, which seemed to match reality a bit better. Distribution substations were placed using the RNM algorithms. Medium voltage topology is good, but we realized there's some pretty big challenges there too. Sort of right off the bat, when we went to use this, we ran into a problem called the wiggles. wiggles meaning not straight lines, but rather this sort of messiness you see on the left. It looks more like spaghetti than a distribution system. And by having to do some work with refining the underlying street map and the line pathways which segments were allowed to follow, we're able to greatly streamline this and come up with much more realistic systems, as you can see here on the right. These are US style systems. And in the US, there's an extensive use of medium voltage, single phase laterals, and in some cases, 2-phase laterals. And then of course, much of the low voltage, these small systems are also then single phase connected from a larger perspective, but often then using a split phase or a plus minus 120 volt system. And so capturing the details of the phasing is actually a non-trivial challenge. In fact, as I'll cite this paper over here on the right, that we go into more details about the approaches that were used in developing these models. But the end result starts to look fairly realistic when in a number of different cases we'll talk about soon. Adding in additional control systems for reconfiguration where switches, capacitors, a voltage management system, including voltage regulators, which exist out on the line. And then on top of that was sort of our next learning experience, which is that the raw synthetic systems coming out of these tools kind of left a number of gaps that were important to fit the needs we had here. And so we made an extensive use of post-processing to add in things like the internal details and switching arrangements of the substations, the control modes that were used for the various devices on the system, as well as to support some of the scenarios, which we'll talk about in just a few minutes. So the next step here is validation. And I'll talk through what we did and a few experiences there too. We started with tens of thousands of distribution system real feeder data from multiple large utilities and some co-ops, and I can't remember, we think we even got one muni's worth of data. So we had large amounts of input to come in here, and we used that to do some statistical validation to compare kind of how our large scale systems looked compared to this large data set of real systems. We also worked with both those data partners and other stakeholders, including some commercial vendors, to say, hey, look, let's get some expert input. Does this look right? And in that process, it started with, well, sort of, it's just a little bit funny. And then after a few iterations, you know, we started showing stuff. They're like, yeah, that looks good. That's how we do it. Or that looks good. We don't quite do it like that, but we know other people do. So yeah, that's great. That looks realistic. And the third part of the validation was computational. In this case, we worked with SIME and EDD, two commercial vendors of distribution software tools, and made sure that when we operated and ran these models, that they behave similar to what we'd see with real systems that are out there in the field, in terms of things like convergence times, as well as some of the technical parameters like voltage ranges and losses, and even though our focus wasn't on some of the short circuit and protection style studies, we did sort of double check a few of those to make sure they weren't too far off. This ended up in a report card, which was sort of based around a more detailed, rich dive around a large number on the order of 20 or 30 different metrics we came up with, where we compared, in this example, 4 of them, and utility validation data on the top across all these regions with our sort of synthetic version here for the San Francisco Bay Area on the bottom. And you can see that more or less these were capturing a lot of the diversity we'd like to see. A report card there too. So a number of experiences, lessons learned within this effort as well. I think the most important one is that statistical validation of these, there's so much variation in the real systems that it's not really a requirement to get a straight A. In fact, we tested one utility of our real data set compared to the full combined data set of utilities, and it didn't pass all the metrics either. So what we did is we realized that if things didn't quite fit within the perfect representation, that it was more of a situation to check and better understand and make sure we had a good explanation and understanding of why something happened. Perhaps it was a more rural area, or perhaps it was some other confounding factor. A number of other pieces that we sort of highlight here, and these are all described in more detail in the paper. Finding a metric was quite important. The idea of a size of a feeder is something we wanted to do. But the way loads are represented in actual models varies a lot, whether some 10A factors have been applied or not, or even if they're included at all, a lot of them are not included. So we found that the distribution transformer rating, kind of the sum of the MVAs of those medium to low voltage transformers, was a more stable way to do comparisons and validation. Anyway, a number of other aspects. Real systems aren't necessarily perfect, so we wanted to make sure that there were still some outliers where the voltages were off in normal operations. And the key piece, of course, is to make sure that we take this validation to improve things as we go forward. So the next step, of course, I sort of alluded to this standardization around scenarios. And so we took a lot of effort in this space to think about a number of different predefined scenarios for solar, for batteries, for even things like fault up locations, electric vehicles, how much is controllable, in an attempt to at least give people a starting point for some standardization for comparisons between different people using this for testing their algorithms. And this led to a few different lessons learned as well. The one was that one of the big ones is there's a lot to do to be quite precise in defining a scenario. And there's more detail. All these tables are available in the paper that describe effectively each sort of dimension that went into these types of scenarios. And I think the other sort of piece that comes with that is if you were to try to combine all of these into, say, scenario 1 through N, you end up with a pretty serious combinatorial explosion. So we took an approach of mix and match layers where each of these are defined somewhat independently, so you can then pick which ones you want to use for a given problem. Like, let's say medium levels of rooftop connected solar with high levels of large scale solar and certain design constraints around the electric vehicles or AMI availability or other dimensions. So where did that get us to? Here's the 3 main distribution test systems that we built. The smallest one over there in brown for synthetic version
Bryan,
of Santa Fe, New Mexico. Where you
keep it short from now? So can you summarize? We're a bit behind.
Yes. Oh, sorry. A couple of technical issues at the top. Anyway, so Santa Fe, New Mexico, this is still pretty darn big. Working all the way up to the San Francisco Bay Area with about 10 million electric nodes. So about 3 or more orders of magnitude larger than what typically are out there. Here's another summary of the San Francisco Bay Area. We made a point of capturing a wide range of different voltage classes and other diversity. That actually was part of our lessons learned there too. One was that we needed to divide things up to successfully build these, and the other is to make sure we had tools to automate these efforts. Here's a summary of those tools. I won't go through all the details here. These are available online as open source. I will highlight though Ditto, which is a many to one to many transformation tool, which we use to extract out our statistical summaries, as well as to make the additions and modifications in post-processing, and finally to put these data sets out in various formats. So final plug is that we are also now in partnership with the same team, in addition to the Texas A&M, working on building large-scale combined transmission distribution data sets that would get from the generation to the transmission system and then kind of combine the same features we just described for the distribution system well. We've already got a small version of these already released for the Austin area. Again, quote small, it's still got hundreds of feeders in it, so pretty big if you're looking for something like that. Anyway, with that, take some questions. And as mentioned, that these models in their current form are available from bettergoods.org and eGrid Data, which are 2 of the RPE-funded data repositories.
Okay, thank you very much, Bryan. Very interesting. We have a few questions. As a chair, I take the opportunity to ask the first question myself. Did you also include missing data and wrong data in your data set? Because I haven't seen any distribution system data that was perfect from the start. So, well, I guess
this is a very good question, Dirk. We did not intentionally introduce missing data. So if your goal is to figure out how good you are at ingesting the challenges that there are when you get utility data, then that would be sort of in our mind like a layer to add to remove some of that, just to kind of make something more realistic. But yeah, we tried to capture the whole thing to make that part easier.
And maybe your experience is completely different
oh no, we pull our hair out every time we get real data, which is part of the reason these things are out there, is to try to avoid, to give somebody a really good place to start with before you have to deal with that.
Exactly. Okay, question from Dan. Are there any tools that make it possible to generate similar networks for other locations, or is it too much manual effort to make that possible?
It's a very good question. The approach we took here was to really focus on developing the highest quality data sets and making those available. So there is a decent amount of manual process in our approach. So we're hoping that by having this diversity of data sets that we get a pretty good place there. I mean, this is all automated. You can't exactly manually line these out. We didn't have an army of engineers design these from scratch. We did automate them, but there's a little bit of manual intervention required. I think there are some people making attempts based on sort of statistics and other approaches to kind of just truly heuristically build things out without necessarily having quite as much, I would argue, care, but for certain applications that can be very useful. Since that wasn't our approach, I think that the answer is we do have tools, but we're kind of in that we probably need to work with you in a particular region to build out new systems to make that stuff happen, because it's not quite a push go.
Okay, very good. Then Raul asks, a very nice work. How are the base networks generated? And he has a second question. Have the networks been validated from some test areas? And what are the metrics for validation and how are they performed? Have you compared distributions of voltages and currents? As with distributions, of course, the mathematical distributions, and do they match well with the existing systems?
Yeah, thanks, Raul. That's a good question. So I went through some of the details here in the steps, but I'll try to summarize real quickly. The base networks are built up using some heuristic algorithms where you start with things like a minimum spanning tree and kind of develop which ones make the most sense from effectively minimum cost, but not guaranteed to be so because it's heuristic based. And there's a lot of detail on the reference network model or R&M tools, algorithms that are used there, including some of the references described here. We start with that realistic load data and then build up the networks from there. And then in terms of validation, as I mentioned, we had this three-part validation approach where rather than trying to take one exact location, let's say San Francisco, rather than trying to say, does our model look like the San Francisco area? That's actually kind of not what we're trying to do, because if we did do too good a job of matching the real system on the ground, then we run into all those sort of data public, can we make this public available? Is it a critical energy infrastructure? Is there any privacy concerns around load data, those kind of pieces? So we're kind of intentionally trying to do, as Tom Overby, our partner on the current T&D space, says, we're trying to make a fictional network, but good fiction. So we want it to look good, but sort of intentionally not quite exactly the same. So as a result, the validation is as we described, where we looked at these distributions of a number of metrics, and there's a lot more detail in the validation paper that's cited here for which those metrics are. We kind of grouped them with everything from looking realistic to performing realistically. And then in terms of the voltages and currents and other, if you will, technical engineering assessment, that was definitely a major focus. We did look at histograms and effectively CDS, with the same idea, like trying to look at the profiles of where voltages laid. In particular was a major focus, given the importance of voltage for distribution, to make sure that those look realistic compared to what we saw with real systems. And so, yes, we did that type of validation.
Okay, then we have one last question to end this session. Do you use satellite images? If so, which resolution, and to detect what?
Yeah, no, Patrick, we actually didn't directly use any satellite images. The only time we use them is to make some things look prettier when we go to display them. I think there might be some satellite imagery used indirectly in some of the parcel data efforts, although I think most of that is based on like county assessor records and those kind of pieces. So when we got it, that had already been pre-processed. Similarly, for the buildings data, there's a decent bit of building representation, like actual building location data available to the OpenStreetMap community. So don't know exactly where that came from, but we just use it in its pre-modified form. And then in terms of well, loads and stuff, that came from ResStock and Comstock, which is a totally different discussion, but described more in paper. But yeah, so we weren't using satellite imagery, although I do know that there are some other companies who are trying to work with that. Of course, one of the challenges with satellite imagery is they work pretty well for overhead pieces, but some considerable fraction of things are underground, especially at the low voltage level, and those get much harder to do. And I think there could be some really interesting opportunities in the future for hybrid approaches, where you take some of this data-driven imagery, data and imagery-driven approaches combined with some of the heuristics that were used here to be able to build out a realistic or actually an actual network for a particular area, which is a little bit different than our focus here, because we wanted to have good fiction as opposed to exactly what's on the ground.
Okay, very good. Then a very final question from Dan, one that I missed is, do you have in your data sets also failure probabilities for lines and transformers and cables? That would be very useful.
Yeah, that's a very good question. Our current data sets don't have that, but they are included in some of our input data. So there is a paper, because we do consider reliability concerns when building up the network. We need to look at that and see if it's a way for us to include more specifics around that as we're officially releasing the data sets. I don't think there's a restriction on that. We just want to make sure it's captured in a consistent way. For now, there's a recently accepted paper that was I described earlier on building the distribution data sets. That was, I'm trying to remember, it's an IEEE journal, I'm trying to remember exactly which one. That we did include some information on the input data, and so that's one place we can get it. But also, for now, you could feel free to contact and we can try to hook you up with that. But it's a good idea for something to include as we put out we're kind of in the release candidate stage for our data sets. And so as part of our final approach, that'd be a good thing to add.
Okay, thank you very much, Bryan, for these answers. And I would like also to thank immediately all the panelists for doing an excellent job in presenting very interesting presentations, the hosts for helping us with setting up the event and playing the recordings, and especially the audience, because I didn't have to ask any question. There were 25 answered questions by now, and plus some questions from the panelists themselves. So I think we had a very interactive session. If there are any questions, please do contact the authors directly via email. I think that's the best solution. And I would say enjoy the rest of the conference. So thank you very much. And with this, I would like to close the session. Thank you.
Thank you, Deep. Thank you very much.
Thank you.
Thank you. Bye-bye.
Bye.
Thanks, Dirk, for organizing. Thanks, everyone. These are great.
Yeah, thank you, everyone. And great job, Ever. Very interesting talks.